Good morning, everyone. I welcome our guest speaker, Mr. Biswas, for the 3-day national seminar on applications of machine learning in electrical engineering. Mr. Biswas obtained his BE in Electronics and Telecommunication Engineering from Indian Institute of Engineering, Science and Technology, PG Diploma in Medical Radiography and Imaging Technology, MBA in System, and MTech in Power Electronics and Drives. Currently, he is working as Scientific Officer E, then in charge engineer R&D. He is qualified in level 3 ultrasonic NDT technique, trained in the design for additive manufacturing and life member of Institute of Engineers. And during his industrial career, few of the important activities are the design of large electrical machine power converters, analysis in FEM and CFD, and his main areas of interest are in induction motor control. So on behalf of the Department of EEE and organizers of this seminar, I welcome Mr. Biswas to deliver the lecture on machine learning for electrical drive application. Over to you, sir.
Thank you so much. So let me start from the, as Madam told, basically my main area of interest is induction motor control. Why I have chosen this? Because this interest grows from my college life. In the power electronics, in the field of power electronics and motor control, one of the famous world eminent person is Dr. Bimal Kumar Bose. So during my college days, he was also the alumni from that same college where I studied. So he used to come, and I have observed that all the branches of engineering is involved in that, in motor control. Means whenever you are designing a converter, you can take first low voltage till 600 volt or 650 volt. So there, microcontroller, the communication, optical communication. Then when you are firing the IGBT or semiconductor switch, there will be some conduction and switching losses that is to be evacuated. So to evacuate that, you have to design the heat sink. Then what kind of cooling is required? If the natural cooling is not sufficient to evacuate the heat, then you have to introduce the force cooling. So these are the things. These are multidisciplinary aspects are involved in motor control. When you are going to inner construction of the motor, the rotor, these are all this high level, high precision mechanical engineerings are involved. So that's why I have chosen this as a multidisciplinary learning, and I hope, in my opinion, this motor control is such a subject which is never ending. Induction motor control, basically. So let us first understand why we should do that induction motor control and what kind of control. So, in when the process and power industries developed in the world, so that time automation and the speed control of prime mover is a very important concern, because a prime mover will be rotating some driven equipment, maybe centrifugal pump, which will be controlling the flow, some fan or some other thing, so on and so on, where the speed control is very important. Now, you can take the combustion engines. You can take an example of our bike or car. Let us take an example, our bike. Okay. So when the roads are very smooth, when we are going through ECR, so, or OMR, the road is very smooth, but the torque requirement is very low. So there we can ride our bike in fifth gear. But suddenly we are entering some bumpy road, bad road, where the torque requirement is high. We cannot ride the bike in fifth gear. It will stall. The machine, the engine will stall. It will be incapable to deliver that torque. So from this example, what we understood that in mechanical prime mover like combustion engines and all, the torque and RPMs are inversely proportional. If you need higher, if you want to, if your speed is low, sorry, if your speed is high, your that means your torque requirement is low. But when the to elevate the torque, when the torque requirement is high, definitely you have to reduce the RPM to do so. Okay, in combustion engines. But in electrical machine, in electrical prime mover, there is an unique uh, advantage where we can control the torque and the RPM in an isolated manner. You can take an example of separately excited DC machine where the armature control and the field control are are electrically isolated. So there, if you control the armature current, your torque can be changed. In the same time, if you are keeping the flux voltage constant, your RPM may not be changing, but your torque will be changed, and vice versa. So here in electrical machine, the torque and the RPM control can be achieved in an isolated manner. So if you see the field of speed control till uh, early 90s and early 80s, the DC, the separately excited DC motors were dominating the field of speed control because it is very easy. You make a converter at the armature side and make a converter at the field side, uh, which will control the flux, the field, and the armature current in an isolated manner, and you can achieve the decoupled control of torque and RPM. But there is some disadvantage in the DC machines because it need it needs brush. So in high power machine, it can create some flash or spark. Okay, because it's a mechanical sliding contact. So it's cannot operate in hazardous area like refinery, nuclear plant, all those chemical industries. There we cannot use. It needs a special design to use that separately excited DC machine in such hazardous places. And moreover, it's not maintenance free. Cost is slightly, not slightly, cost is more. So to overcome these things, when in the market, the induction motor evolved, so it's very robust in design, simple in construction, more or less it is maintenance free, and it can, foremost, it can operate in hazardous environment. Due to this reason, the concept of speed control, people are rushed over on induction machine, how to achieve that decoupled control there. But it is not so easy, likely to a separately excited DC machine. You can take an example. When our ceiling fan is rotating or our stand fan is rotating, basically the energy from the electrical domain, it is going to mechanical domain. The electrical domain, the energy in terms of voltage and current, it is going to mechanical domain, which is rotating the fan and producing some RPM and the torque. Okay, this is simple thing. Now 230 volt, voltage is more or less constant. Mainly current is going. We are changing the current through regulator and the speed is changing. So basically I can infer, I can write down one statement that the input current is converted to from the electrical domain, the input current is getting converted to RPM and torque. For a certain instant, it's drawing 3 ampere of current. Now, if I ask from that 3 ampere, how much is going for torque production and how much is going for RPM flux production? Is it possible to isolate? The answer is simply no, because if it was a separately excited DC machine, for the fan blade, say connected with a separately excited DC machine. Now by changing the flux side, I can control the speed somewhere. And by changing this, I can control the torque also. But in induction machine, it is not possible because the rotor is getting induced, the rotor is getting magnetized from the stator field and it is lagging. The speed, the resultant flux of the stator is rotating in the stator space. It is the rotor is not able to catch that speed exactly. It is slightly lagging. That is called sleep. Okay, that's why it is called asynchronous. The speed which the stator flux is rotating, that is called the synchronous speed. From that, rotor is getting magnetized. There will be some delay. Due to that, it is not exactly catch that. But if it is a permanent magnet, already rotor is magnetized. No need to do anything. It is perfectly locked with the stator field, which is called synchronous machine. Anyway, those are the different kind of construction of the electrical machine. But today we will concentrate only on asynchronous machine. So what I was telling that it is very difficult to decouple it. The current which is producing flux and which is producing torque. That means we want to analyze an induction machine, a synchronous induction machine, analogous to a separately excited DC machine. So if you're able to do that, then I can operate the asynchronous induction machine also as a separately excited DC machine, which is called vector control of induction machine. So for what we have discussed, the thing is why I told this story, because we need some specialized application like paper mill. If you have seen any paper mill, I have seen. I went that on paper factory here. What is that one local newspaper factory? When the pulp, the papers are coming out, if the dynamic response, if the torque and the RPM dynamic response is poor, what I am meaning to tell, if the dynamic response is poor, that means, say now the machine is rotating at the RPM of 500. I am suddenly changing it to, I am giving from the steady state, I am giving a step response as excitation of 600. So if to achieve that speed, if there is an undershoot and overshoot, and it is not synchronized with the torque requirement, what will happen? Naturally, you understand that it is try to follow, but there will be some transient behavior. If the transient is more, your dynamic response is poor. Immediately the paper it tear out and the entire pulp will go waste. So in such case, your dynamic response of the prime mover should be very, very accurate. Okay, there should not be undershoot, there should not be any overshoot. It is perfectly, nearly sharp increase. The rate I have changing the excitation, the output response of the machine nearly will follow the same path. That means the dynamic response of the system is very good. So we have to make such thing. It's even though the construction of the machine is quite easy, but the task of a control engineer is become much more difficult. So today, what we will understand, what we will learn, how to what is the basic concept of the vector control, how it is to be implemented, and there is some from the classical concept, when we are going in broad aspect to improve all the dynamic response of the machine, that time we need to do some model free analysis. Always that analytical concept, classical analytical concept may not work, because some things are dynamic in nature, random in nature. So all those cases, we need to have dynamic learning of the system parameters, and it is to be updated dynamically to compensate the change of some passive parameter of the machine to maintain the desired dynamic response of the prime mover. Where we will go, we will just understand the as I told, the induction machine, the vector control of induction machine is nothing but to implement a separately excited DC machine analogy to an induction machine. So now, you know, this is the very simple, very simplified equivalent circuit of a separately excited DC machine. So this side your armature side, and this is your field side. And you know, this angle, the construction is such that the armature flux and the field flux, they're aparted by 90-degree angle. So now cos 90 is 0. So there is no influence of armature flux on field flux, and there is no influence of field flux on armature flux. This is a decoupled nature. And if you see the governing equation, the torque basically, it's a product of field and the armature current. And the back EMF, you see, it is irrespective of armature current. It's a very interesting thing. By the virtue of its construction, the back EMF of the machine is independent of armature current. And the torque of the machine is independent of omega. There is no omega. And there is no armature current. This behavior make a separately excited DC machine to operate in a decoupled manner. I'm going very slowly because you should, most of the student and I have seen they are thinking that vector control is a very big thing. Yes, it is slightly difficult, not difficult I can tell, but your conception is it is to be that your conception should be very, very clear. It's not a very big thing, what I feel. So there is some transformation. I am not hope you have already studied that Rajan, uh, uh, Rajan, I'm in a seminar. Okay, I after 11:30 I will talk to you. So this is a simple phasor diagram. What I was telling that Park and Clark transform. Hope all you know that it's not a big thing. I will explain here very quickly. So you know this is your R phase, this is your Y phase, and this is your B phase. Now from the three phase, you want to convert to two phase. So this angle is 90 degree. So this is your alpha axis, this is your beta axis. This is the stationary axis. Okay. So the alpha axis, this alpha axis is reference axis, which is just lying on the A phase or R phase. This is B phase, this is C phase. Now it is aparted by 120 degree. So if I take a current, so I alpha is equal to IA cos 0 plus IB cos 120 plus IC cos 240. So this is the beta axis. So your I beta is equal to similarly IA sin 0, IB sin 120 and IC sin 240.